Hello everyone, welcome to the lab. Test equipment repair time again. This is Hewlett-Packard E4421B signal generator from 250 kHz up to 3 GHz. I picked it up on eBay. It was listed for parts or repair and I made an offer, $200, and it was accepted. And I paid almost $50 on top of that for tax and shipping. Not too bad for this sort of an instrument, but it was listed with a big problem, namely missing power supply. And in my view, it's a very bad sign. First of all, because it might mean that something is really wrong with this unit, so someone decided to use it for parts. On the other hand, it also can be very difficult to get one. Here is the back of the unit, and when I received it, I was glad to see in that hole that the power supply seems to be there. So it's a better deal than I thought, and what seems to be missing is a connector here. And these connectors usually have filters built in, some capacitors and inductors. So can it be something simple, like a failed filter, and someone took it out to get a replacement and never got around to putting it back in? Or maybe something is seriously wrong with this unit and someone decided to use it for parts or something like that. Let's not guess too much at this point. Let's take it apart and have a look. This unit has an option, 1E5, which is a high stability time base. A calibration sticker here, last calibrated in 2013. The cover is off, and as you can see, the power supply seems to be there. But the metal work is all around it. So I'm not quite sure how far this unit should be taken apart to work on the power supply. So I unscrewed this internal cover and we can have a look inside. Here is the main board and it looks fine on the first glance. I don't see any missing parts or any damage. And the power supply is here. And it seems to me that all three sides, at least, are made of a single sheet of metal bent like this. And this side extends all the way to the front panel. So I'm still not sure if it is easy to just unbolt this whole thing and lift it up or not. Let me try. I unscrewed this cover on the bottom and look at this dent here. And there is no dent on the external cover. So why is that, I wonder? What's going on here? So now we can partially see the power supply. So here it is. It was not too difficult to remove it. Look at this dust here. So now we should be able to unscrew these standoffs here and these heat sinks and slide the board right out. And look at this dusty fan. And here is the power supply board. I used compressed air to blow the dust out, so now it looks much better and I don't see any problems so far. Let's check the fuse. No problem. I happen to have this connector with EMI filter built in. Delta Electronics, new, never used. It must be just like the one which is missing. And I don't have a connector like this, but I found this in my junk bin. This was a power supply from a VCR or DVD player or something like that. I don't even remember. I took it apart a while ago. And someone cut the power cord before tossing it out. I never understood why people do that. And as you can see, I already desoldered some parts from it, like electrolytic caps and such. So this connector is slightly different, but it has the same distance between the pins. So I'm thinking about desoldering it from here, putting it there, and I can reuse the wires. Perhaps I will need to extend them a little, and I will need the ground wire as well with a crimped lug to bolt it to the chassis. So I'm tempted to put this back together and give it a go. Prepared the filter for installation with extended wires that should reach the connector and the ground wire, and replace this connector here. Whoever removed this connector carefully saved both screws, one here and one there, and this nut on a grounding post. Thank you very much. And hopefully I can install through this hole and I don't have to remove the back panel. Let's see. The ground is attached. There you go. The connector is in place. It turns out that screwing in the filter was a little premature, because when it is sticking out through that hole, it is on the way of the power supply installation. So it should be screwed in after the power supply is in place. Done, and straightened out this dent a little just to make sure it wouldn't touch the board. Plugged it in, and the standby light is on, which is a very good sign. Let's give this a go. There you go. It's booting. Very cool. The screen flicker is on camera only. Here we are. It booted up. So far so good. These LEDs show the status of the power rails, and they all light up, so power rails must be fine. Only one error here, oven cold, which is expected. This is about the high stability time base not being warmed up. The error will disappear once that happens. I brought my spectrum analyzer, and we are looking at 3 GHz 0 dBm signal, and unfortunately it is too low, minus 16 dBm. So something must be wrong with this unit. I checked on different frequencies and I saw the same problem, about 16 dB lower output. So here is my idea what to check next. I removed this side cover, and here we have 3 RF modules, synthesizer, time base and output amplifier. And I believe these modules are identical across this whole family of instruments up to 4 GHz. And I have a similar signal generator which can go up to 2 GHz. So I can either put these modules into that instrument or the other way around, and this should help to narrow down the problem. I moved the modules into my 2 GHz instrument, and I'm almost sure they are fine, otherwise we would see some error like unlevel or something like that. I believe there is a power sensor for output leveling somewhere close to the output from this amplifier, and the problem must be somewhere after that, let's say in the output attenuator. But let's make sure, because it's easy. Here is my 2 GHz generator, and by the way, I have a video about it and why the screen looks the way it does. I'll put the link in the description. So again, we are looking at the 0 dBm signal at 2 GHz this time, and we have about -1.5 dBm, which is okay because of some loss in this cable and adapters. So this looks just fine, no problem. So I believe the problem must be with this step attenuator. Here is the output from the amplifier module there, and it goes this way and into this attenuator, and this is the output which goes straight to the front panel connector. So there is almost nothing else that can be wrong besides the attenuator. There's a small chance, of course, that let's say this rigid coax can be broken, or this one, but they look good. So perhaps we can check right here, and if it's fine, we should swap the attenuator from the working unit. So checking the output right from the attenuator, and as expected, almost exactly the same thing, -17.5 dBm. Must be a little more loss in this cable. So let's swap the attenuator. With attenuator from the working unit, we have no problem at all. -0.95 dBm. Perfect. So here is our problem. I took the cover off this module, and it seems like I need to undo these screws to take the board out. Here it is. I took some pictures, let's have a look. This is the input connector, and here is the other side of it, and this mates with this connector into this magic block. Here it is, Agilent 1GM1-4200, and this is where actual attenuation happens. This pin must be the output from it, and it goes this way into this output connector, and this goes through a rigid coax to the output connector on the front panel. This section must be about reverse power protection. If substantial power is fed back through this output connector, it goes through this reed relay first, then it meets these DC blocking capacitors, and then here there are two power sensing diodes, one on the positive side, one on the negative, I would think. Then there should be some comparator, perhaps this one, so that if the power exceeds some threshold, this reed relay is disconnected. Now let's have a look at this attenuator. How many pins we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 pins to control this thing. This pin must be ground, and this one I am not sure. Is it even connected? I think it can be seen here in this hole. So it's not clear what this pin is. Anyway, 14 pins to control this thing, and 7 filters here, and 7 more filters on this side, and 7 labels. And these must be about attenuator pads inside of this thing, 5 dB, 10 dB, 40 dB, and this is one set, and another set here, 5, 10 and 40, marked with B, and just one 20 dB pad. and all these add up to 130. So this thing can attenuate up to 130 dB in 5 dB steps, and finer control within 5 dB must be done somewhere else by some other means. Now let's have a look at this section. We can see 3 power rails here, 5 volts, 12 volts and negative 12, and also trip and reset, and these must be about reverse power protection. Here we have 7 analog switches, and they are DG413DY, and not much more. So I think I removed this attenuator from the instrument too soon. I should have experimented a little bit with different output levels just to understand better what's going on. And this is not a problem, we can always put it back in and experiment some more. Or maybe experiment on the bench, hook this thing up to a bench power supply. It should not be difficult, just 3 power rails and some simple digital control. And here I found a block diagram of this attenuator. These instruments can be equipped either with a mechanical attenuator or with an electronic one. We have an electronic one here. And here is the input, 7 pads, reverse power protection limiter. And here's the output. The threshold here is 27 dBm. The relay is driven by 5 volts. And here we have 3 power rails, trip and reset, and 7 control lines. I would think 5 volt TTL level compatible. This makes perfect sense and matches what we have seen so far. I traced the pin out, which was quite easy, and I found a suitable connector. All inputs here are pulled up to the 5 volt rail using pull-up resistors, so they are activated by pulling them down to the ground, which makes perfect sense. Let's test this thing. Here is my test setup. This Tektronix power supply is going to provide 3 power rails, and I double checked and triple checked my connections, so hopefully I did not make a stupid mistake. And I'm using this breadboard to control the attenuation pads. Here is the ground, and this blue bus is grounded. So currently I pulled down to the ground all 7 inputs and I labeled them here. I believe the default state when all these inputs are pulled up to the 5 volt rail inside of this module is the maximum attenuation, and this way I believe I selected 0 attenuation, and then we should be able to enable and disable a particular pad. I made the extra effort here to make it nice and clear for this video, so hopefully it is easy to follow what I'm doing. And I prepared these instruments here. There is a coupler in place of the attenuator for now, and I'm generating 1 GHz, and I entered this offset here for the amplitude minus 2.1 dB, so that we read exactly 0 output here and 0 input here. So now let's remove this coupler and connect the attenuator. So let's enable the output here and turn on the power supply. What do we see? Minus 5.42 dBm. Huh? I wonder why is that? Based on what we've seen before, I would expect about 16 dB error, but it is about 5. Anyway, let's try different pads. 5A, almost exactly 5 dB difference. 10A, 10 dB difference, 40A, 40 dB difference, great so far, 20 dB difference, 5B, exactly 5 dB difference, 10B, 10 dB difference, and finally 40B. 40 dB difference, wonderful. So the attenuation pads seem to be okay, and that means the magic Agilent block, which is the core part of this module, is most probably okay. And if so, it is very good, because it is most probably not repairable and not available. But still there is some problem, and I wonder what's going on here. I reconfigured my test setup to use this function generator, so we can test both attenuators at 10 MHz, and I set the amplitude here so that we read almost exactly 0 here with this coupler again. Now let's try. This is the attenuator which is suspected to be faulty. Let's turn it on. What do we see? Minus 4.8 dBm. And check this out. This is the good attenuator, and we see about the same minus 4.9 dBm insertion loss. So it seems like there is no problem with the attenuator at all. So what was wrong then? Perhaps some connection was bad? I did not feel that any SMA connectors were loose when I removed the attenuator. Or maybe it's because I reseated the internal connection. I'm not sure. So let's put it back and test again. So the original attenuator is back in place and everything looks great. 3 GHz 0 dBm output, and we are reading minus 1.73 dBm here, which looks about right for this cable and adapters. And we can try, let's say, at 1 GHz and 1 gig here, minus 0.75 dBm. This looks perfect. Unfortunately, it's not clear what exactly was wrong with the attenuator, and it's hard to be sure that this is fully repaired. Maybe there is something intermittent, but so far it looks perfect to me. And if you think I was crazy buying this thing with presumably missing power supply, yeah, you are right, it was crazy, but it worked very well. I am quite happy with the result. This is how I get better and better equipment for my lab. Thanks for watching. Bye.